I push the button start recording. Okay. Oh, there are only 3 people today. Oh, it's strange, very strange. Okay, it doesn't matter. So today I'm going to discuss 3 topics. I decided to split the whole tutorial into 3 subsections. I think it's going to be more convenient for everyone. So the first topic, it will be sort of introductory. I want to introduce you the concepts of modal and spectral matrices. It's just definitions. So let's write down our first topic, the name of our first topic, modal and spectral matrices matrices of a given matrix A. So, of course, if you watch the lectures, you're already familiar with this concept, but nevertheless, it never hurts to go over this topic once again. So let's start out with definition. To save time and ink in my pen, I'm gonna give you a definition only for matrix 2 by 2, just for clarity, for brevity, and so on. But of course, it can be generalized to any square matrix. So let's imagine that we have matrix A. No, 2 by 2, but it can also be 3 by 3, 4 by 3, and so on. And let lambda 1, lambda 2 be eigenvalues of this matrix. Eigenvalues. You know how to calculate them. We did it for the whole last tutorial. And also, let E1 with components x1, y1 be the first eigenvector, and E2 is the second eigenvector. Let's denote its component like x2, y2. And remember that each eigenvector corresponds to its own eigenvalue. So the first eigenvalue was lambda 1, so it has vector I1, and so on. The order matters. In linear algebra, order matters all the time. So what next? So then modal matrix is denoted by capital letter M, and it consists of components of eigenvectors put in the same order. So the first column will be the first vector, E1 eigenvector, and the second column will be the second vector, E2. That's it. So this is the definition of the modal matrix. And now, as for spectral matrix, it's even easier. Spectral matrix, it's denoted by capital lambda. So the ordinary lambda was like this. You're already familiar with this, but the capital lambda looks pretty different. It looks like a triangle or something. So this matrix looks like this. Look at this: lambda 1, 0, 0, lambda 2. So you can clearly see our familiar guys, eigenvalues here, but they are arranged in a special order. So let's look, and this matrix is closely connected with matrix M, modal matrix. So look at this. Here in matrix M, we had the first column vector E1. It has value I1, value lambda 1. That is why this column is put in the first place. First column here, first column here. They should correspond. And at the same time, it should be diagonal matrix. These lambdas are located only on the main diagonal of the matrix, and the rest of the entries are 0. So this is a spectral matrix. As you can see, things are pretty easy. And of course, in the case of 3 by 3, we can write it in parentheses. So if you have case 3 by 3, then your matrix will look spectral matrix. Spectral matrix will look somewhat like this: 0, lambda 2, 0, 0, 0, lambda 3, and so on. So all these lambdas should be on the main diagonal. Okay, so I think it's better to go for one of the examples. So for example, let's take problem 1a from our tutorial sheet, and take the matrix from there. So matrix is very easy, 2 by 2. Unfortunately, our tutorials are so short that I never have time to deal with matrices 3 by 3. So in this question 1, you have also 2 more matrices, B and C, and they are both 3 by 3. But unfortunately, I can't waste my time on them. I think you can easily do it at home, but because you got the idea now, and that's all you need. So I'm only going to demonstrate it by this small matrix. So we need to write out these matrices. And of course, according to definition, you immediately guess that you need to do the same procedure as in the last tutorial. You need to find eigenvalues and then eigenvectors. But you know, in this particular task, there will be some new things for you as well. Okay, just be patient. Let's do the first step. The first step is about finding eigenvalues. So if you remember, we need to subtract lambda from diagonal elements. Put vertical bars, showing that we are dealing with determinant now, not the matrix, and set it to equal to 0. This is called characteristic equation of our matrix. So now we need to calculate our determinant. Oh, very nice formula. Look at this. You can explicitly see a squared minus b squared. That is why it's better to do factorization. I'm not going to use determinant this time because it doesn't make sense. Look at this. It's much more beautiful to do it this way. And I immediately get two lambdas. The first one is -1 and the second one is 3. So we already get eigenvalues, and that is why it's quite easy. We are already prepared to write out this spectral matrix. It will look like this. Again, I'm just reminding you, in our particular case, it will look like -1, 0, the first column, and the second column will be 0, 3. So that's it. Half of the task has been done. Now it's time to switch to eigenvectors. It was a week ago. Maybe you could have forgotten how to do it, but my duty is to remind you. So to find eigenvectors, we needed to use this general equation: A, matrix A, minus lambda I, times identity matrix, we are closing the sign of the matrix, times our current EI eigenvector, and it's all equal to zero vector. So this was the equation, concise form of the equation for finding eigenvalues. What does it actually mean? So this subscript index I means that just substitute your current lambda. You have two lambdas already they've been calculated. So just substitute it into this matrix equation, and this will be unknown this time. This is eigenvector. This is our goal. But you know, what I did last time, I expanded. I wrote out this matrix in more detail, because this is just, symbolic expression to make formula look very concise and beautiful. What it actually means, what kind of idea is hiding behind this notation? It means that just subtract lambda from each diagonal element. And we did it before. Look at this. This is the matrix which we need. So I can just copy this matrix here. Unfortunately, I can't put them both into screen. So you need to believe me that I'm copying it correctly. So this is the matrix which should be here. And the only difference, we can put index I here just to be mathematically rigorous. Then, so these are all numbers because we already know lambda. We already calculated in the previous step. And the next step is to expand coordinates of this guy, which has only two components, and finally is equal to 0, 0. So this is our general equation. Now it's time to go over each lambda one by one. So lambda 1 is equal to 1. It means that we need to take this matrix and substitute -1 there instead of this lambda. So 1 minus -1 will be 2. The first row is 2, 2, and the second row is the same, 2, 2. And last time I gave you very long methods: Gaussian elimination, reducing matrix to row echelon form, then finding leading elements, and so on and so on. And you know what? I did it deliberately. I wanted to convey you the idea that this Gaussian elimination method, this algorithm, will rescue in any situation. It's very reliable, highly reliable. But sometimes you might get so frustrated by it because the task at hand could be so easy, just like this, just like now. And it looks like, if you try to use Gaussian elimination, it will be like a waste of time, probably, or waste of effort. That is why it's time. I think that after the previous tutorial, you are ready to get more advanced. So in the case of 2 by 2, you can solve this problem in a much quicker and more efficient way. So it's time for you to discover this secret, this trick for you. So look at this matrix. You can see that the second row is just exactly the same as the first row. But if you remember that every row corresponds to its own equation, it means that these equations are actually the same. It's actually the same equation, so we don't need the second equation. What's the point? It's the same equation. And that is why, instead of using Gaussian elimination and everything, we can just get immediately back to the system, or rather to one equation. So this first row corresponds to this equation, right? Of course. And of course, look at this equation, you immediately guess that, oh, it would be nice to divide everything by 2, of course. And I also prefer to express y in terms of x. And you know what? We ended up having only one equation, very nice equation. And all we need to do, we need to find some couple of numbers, x and y, to satisfy this equation. Or you can immediately see that if I put x 1, for example, then the y will be -1. Well, of course, you can come up with another pair of numbers. For example, 2 minus 2, or maybe -2, 2, or maybe 10 minus 10. It doesn't matter. Everything is correct. So it looks like these are already coordinates of our eigenvector, sorry, 1 minus 1. So this is the shortcut. This is the much nicer method for finding eigenvectors. But remember, it only works for 2 by 2 matrices. Unfortunately, the bad news is that for the case of 3 by 3, you have no option. It's always better to use Gaussian elimination because you will never guess, how many equations are left after Gaussian elimination. Sometimes it's only one equation, sometimes 2 equations. In this case, everything will be different. So unfortunately, this trick works only for 2 by 2. But nevertheless, it's better than nothing. Okay, so now we can do the same. We can practice our new trick, our new knowledge on the second lambda. So lambda 2 was equal to 3. To 3. And let me, again, I need to get back to this matrix and substitute 3 instead of lambda this time. So minus 3 will be -2, 2, 2, -2. -2, 2, 2, -2. This time, these rows are not equal, like in the previous case. But you know what? They're proportional. They are linearly dependent, as mathematicians say. Look at this. How do we get the second row from the first one? Very easily. We can just multiply the first row by -1, and we immediately get the second row, which means again that these are representing the same equation. No sense of repeating them. So, getting back to the equation, we obtain even better equation. Look at this. Again, I divide it by 2. And if I express y in terms of x, it's even easier. You can maybe see that numbers 1 and 1 satisfy this equation. So these are the coordinates of our eigenvector. Nice news. So very nice. So I have no doubts that you all like this trick. Okay, and last time I did it deliberately. I did it. I wanted to torture a little bit with this Gaussian elimination so that you would understand that it's a very good method. Actually, maybe it seems to be long at some situation, but it's very reliable. If you come across a very strange situation, very unusual, you might get confused. But Gaussian elimination will always save you. So just know about it. Okay, this was this. Okay, so it's time, and now we are ready to write down our model matrix. So model matrix consists of these eigenvectors put in a special order, in the same order as in spectral matrix. So that's it. We are finished with this task. And one note. These two matrices, model and spectral matrices, they have a connection between them. A connection is given by a very nice formula. So let's write it down, because sometimes you may be asked to write down this formula, to use it, to apply it, and so on. So the connection looks like this. So this is very famous formula. So, and I think that, yeah, in your tutorial, even you have a question 2 probably. No, in question 1, actually, we are not finished with the question 1. You are asked to check this equation. But unfortunately, in tutorials, I'm not going to do this because it takes a lot of time. No. But you can easily substitute your information here and check that it holds true. Okay, so we are finished with the first topic. As you can see, we haven't done anything special. We just, got familiarized yourself with this concept of modal and spectral matrices. Okay, now it's time to do something more concrete. So the second topic is about matrix powers. And there are actually two methods. So I put it in parentheses. Method 1, matrix powers. Method 1, matrix powers. Method 1. So just imagine that you are given matrix A, square matrix A, and you are asked to find the square of this matrix, A square. How would you do it? Of course, you will multiply this matrix A by itself once time. If you are asked to find the cube of this matrix, you multiply it 3 times in a row. But if you are asked to find the matrix A to the power of 100, of course, no, you will say that, no, thank you, I'm not going to do this because I don't fancy multiply matrix 20 times in a row or 100 times in a row. There should be some nice method, some nice formula or algorithm or something. Okay, so introductory note: if your matrix has a diagonal form, we have a spectral matrix. Okay, let's consider spectral matrix. So let's consider spectral matrix. It has a very nice form, actually. It's called diagonal form, when all the elements except for diagonal ones are zeros. It turns out that if you start playing with this matrix, trying to find the powers of this matrix, then you will discover quite an amazing thing. So lambda to the power of n will be lambda 1 to the power of n, 0, 0 again, and lambda 2 to the power of n. Very nice fact, very nice fact. So you need just to take to the same power all these elements which are on the main diagonal. In this case, in our case, they are of course eigenvalues, but it's not necessarily being eigenvalues. Okay, but unfortunately, not all the matrices have this beautiful diagonal form. What do we do in the general case? And it turns out there is a very nice formula. So let's write it down. If A is just square matrix, 2 by 2 matrix, 2 by 2, 3 by 3, 4 by 4, and so on, then luckily there is a very nice formula. So A to the power of n is equal to m, modal matrix, times lambda to the power of n, the same power as here, and times m inverse. So as you can see, a very nice formula. Luckily, we have this formula. But if you look at this formula closely, you realize that a lot of work for us is hiding behind this, this formula. Before we can apply this formula, we need to prepare this model matrix, which means that we need to calculate eigenvectors. Okay, and this my m inverse means that we need to find m inverse. But as for this guy in the middle, it's quite easy. It's quite easy. And I need to make a little note immediately because this formula looks pretty similar to the previous one, which I just mentioned in the previous topic. So note, don't confuse this formula with the previous one. They are very similar. It's always very dangerous when some formulas are very similar. With this formula, previous one, do you remember? I just gave it in the previous page. Lambda is equal to m minus 1 am. Look at this. Very similar structure in the right-hand side. Very similar. And this is the danger. Look at this. The difference is that here matrix M is in front and here M inverse in the front. Just make note of this difference. Very, very important. Otherwise, it will be very frustrating if you lose marks only because you confuse the order, because you remember things quite vaguely. Okay, and so as you may guess, we need to apply this formula. You know, the beauty of this formula is that it can be applied to matrix of any size, 2 by 2, 3 by 3, 4 by 3, I don't know, 20 by 20, and so on. So, but unfortunately, again, due to the lack of time in the tutorials, I'm going to demonstrate you how it works for the case of 2 by 2. Even this will involve a lot of operations. So unfortunately. Okay, so it's gonna be problem 4D from our tutorial list. Question 4D. So we have matrix A there, which is 4, 3, 1, 2, and the assignment is to calculate a to the power of 20. Sounds like very serious assignment. Okay, let's rewrite our beautiful formula for our situation. What do we have here? So according to this formula, which I just gave you at the previous page, this one. So we need to write it a to the power of 20 is equal to m times lambda, spectral matrix, to the same power of 20, and m minus 1. So this will be our guiding star. We need to prepare everything to be able to use to apply this formula. So the first thing which we can do, we can find eigen values, and after that we'll immediately can write this guy. Okay, the first step 1 will be calculating lambda 1, lambda 2, and consequently lambda to the power of 20. Let's do it. It's the easiest step, the shortest one, probably. Okay, so 4 minus lambda 1, 3 time minus 2 minus lambda is equal to 0. I'm just using my initial matrix, and I'm subtracting lambda from each diagonal element. Okay, next we need to expand this. 4 minus lambda, 2 minus lambda minus 3 is equal to 0. I know how to save a couple of seconds. I'm not going to solve this quadratic equation, even though it's quite an easy task. I'm just going to give you the roots immediately. Maybe we will save 10 seconds in this way, which is quite nice anyway. Okay, so after that, we can write our lambda. Lambda is equal to 1005. This is our spectral matrix. And there's nothing easier than to take the 20th power of this spectral matrix. It will be 1 to 20, 0, 0, and 5 to 20. And of course, it's better to rewrite it because 1 to any power is still 1. 1, 0, 0. And as for 5 to 20, we have to leave it as it is. I don't think that anyone fancies calculating it. Oh, no, it will be a terrible number. Maybe billions, maybe more, no idea. So we don't need it actually. Okay, so this is our first result. This is our middle term in this formula. So we are ready to write down this middle term, but we still don't have this guy. Okay, so it will be our step 2. Step 2, finding eigenvectors e1, e2, and after this matrix M. So let's start with the first one. As always, we need to write down this matrix. 4 minus lambda y, 1, 3, 2 minus lambda y. This is a matrix which we are going to use. How did I obtain this matrix? I just copied it from here, and put a lambda I as index and subscript. Okay, but I'm running out of page. Unfortunately, I need to adjust something. So I want this guy still to be in the field of view. It looks pretty nice. Okay, and now we will go over this matrix, one by one. So our first lambda was 1, if you remember. In this case, this matrix look like 4 minus 3 will be 1, 1, 3. Oh, something went wrong. I made a mistake. Very tragic. Something is not working. Because you know how determined that I had a mistake? That these rows should be proportional, and they are not. What happened? My goodness, I don't know. What is so frustrating, and time is running out. So okay, 1, 5. So 4 minus 1, no idea. But there's definitely a mistake. Because it's 3. My goodness. Maybe I haven't woken up properly. Of course, 4 minus 1 will be 3. I got really scared because time is running out always. This is my main issue. Okay, that's nice. And now you are not scared of doing this task in the list because we know this wonderful professional trick, I would say. Look at this. These rows are equal. That means that we don't need the second row, the second equation. We can immediately get to the equation instead of the row. Okay? Oh, it's better to express y in terms of x to make things more convenient. And of course, we can easily see that if we put x is equal to 1, y will be minus 3. So this is our first eigenvector as a result, 1 minus 3. Here it is. Very, very quick and efficient way. Okay, the next, lambda is equal to 5. Lambda is equal to 5. Again, look at this matrix. We substitute 5 here. So 4 minus 5 will be minus 1, 1. Minus 1, 1. And here we get 3 minus 3. Again, the same story again. The second row is repetition of this first row because it can be obtained by multiplying the first row by what? By minus 3. Okay, so it corresponds to minus x plus y is equal to 0, y is equal to x, and our second eigenvector will be just 1, 1. Very nice result. Very nice numbers, I would say. So now we are ready to finish our last step, which was devoted to finding model matrix M. So M, the first column will be the first vector, eigenvector 1 minus 3, and the second column is 1, 1. So this is the end of step 2. We found the model matrix. And now it's time for the third step. You know, the bad news is that we are not finished. We are not yet quite ready because we have this guy M. We have this guy during the first step, but now we need to find the inverse of the matrix. You know, in my previous tutorials yesterday, I was tempted to skip this step because everyone is familiar with the process of finding inverse matrix. But students nevertheless asked me to repeat this process. That is why I think it's better to do it. Okay, it won't require a lot of space. I think it will be enough, this space. So step 3 will be finding m minus 1. Okay, but I need to, m is just in front of my eyes. Okay, it's another algorithm, very short one, but nevertheless the algorithm. The first step is to find determinant of a. Determinant of a is 1 minus 3, 1, 1. So it's equal to 4. The second step is finding a matrix of cofactors. So each element, each entry in matrix M has its own cofactor. How to find these cofactors? It should be reminded, of course. You know what? I prefer to write out this matrix of associated signs, plus, minus, minus, plus, just for convenience. So these signs reflect the locations of each element and how to deal with signs. We are going to discuss it immediately. So let's just start out doing. So the first element is 1 in the top left corner. How to find its cofactor? The answer is you need to cross out the row and the column where this element is located, and you are left with this 1. And after that, you immediately look at the position side. Plus means that multiply your result by plus 1. It doesn't change anything. So 1 is the final result. Okay. So, but the next element, this element, will be more interesting. So again, it's located in the first row and the second column this time. So we cross out these two guys, and we are left with minus 3. Minus 3. So remember, minus 3. But the position matrix says multiply this result by minus 1. So we got minus 3 times minus 1. We need to change the sign. Plus 3. It will be plus 3, and so on. So for minus 3, we cross out these rows, and we get minus 1. And for 1, we get just 1. I decided to save a couple of seconds, just not discussing it in too much detail. Okay, the third step is transposing matrix. So M star transposed. It's a very easy operation. So how it's being done? Oh, where's my? You see my image? It disappeared. Oi. Oh, it's a catastrophe. What shall I do about it? Maybe I should leave the tutorial and come here again. Oh my goodness. It's a very nasty surprise. It happened all of a sudden. Maybe something is wrong with my camera, but it didn't let me down before. Yeah. Too bad. Okay, so what I'm going to do, I'm going to leave this tutorial and then come back, okay? Maybe this will work. Okay. Oh, thanks God, it's working. And it's still being recorded. What's curious about it? Okay, such a relief. I got really scared. Of course, I can always record this tutorial, but it's better to explain these things now. Okay, so what this transposition means? It means that the guy who was the first column, for example, it becomes the first row. So 1 minus 1 becomes the first row. And similarly, the second column is becoming the first or the second row, sorry. And the final step, I'm going to write it here, is to calculate eventually this inverse of matrix. There is a formula, 1 divided by determinant of M times matrix we just obtained in the previous step. So it will be 1 over 4, and this matrix we just rewrite it here. And I think that we can leave this result in this form. I don't think it's good to try and multiply every element by 1/4 because we will get factors, and factors look ugly. It's better to avoid dealing with factors. So now, after these 3 steps, we are quite ready to do what? To substitute all these results in our spectral formula. So it's going to be step 4, the last one. Step 4. Step 4. Using formula class, I'm going to rewrite it here once again. So a to the power of 20 was equal to m times lambda to the power of 20 and times m inverse. So let's substitute all these guys here. So matrix M look like 1 minus 3, 1, 1. Lambda to the power of 20 was obtained in the very first step. It was 1, 0, 0, 5 to 20. And the last matrix was obtained just, a minute ago. It has a factor 1 over 4 in front. I think it's better to move it here, just in the very front of everything. Okay, 1, 3, minus 1, 1. And now we need to perform this multiplication of matrices. Okay, let's do it. I'm tempted to skip this step, but some people get confused with this terrible guy. That is why it's better to do it. Okay, I'll spend maybe a couple of minutes. I'm really curious about how much time I'm going to spend on it. Okay, so first of all, we need to multiply the first 2 matrices. Let's do it. Let's remember how we did it. We take the first row here and the first column from here and multiply them like this, 1 by 1 plus 1 times 0. It will be 1. Then, again, we are using the first row, but the second column this time. So 1 times 0 plus 1 times 5 to 20. It will be 5 to 20. Now it's moved. We spent all our columns here. That is why it's time to move to the second row in the first matrix. Minus 3, 1, and start with the first column again. So minus 3 by 1 plus 1 times 0 will be minus 3. And finally, the last row and the last column here will give us what? It will give us 5 to 20. Okay, and I'm rewriting the last term, the last matrix. Okay, Now we need to multiply these 2 matrices. These 2 matrices. Okay, the same process, the same procedure. First row from here, first column from here. So 1 times 1 plus 3 times 5 to 20. And this is our final result. We are not going to simplify it because it's possible. We don't need to calculate 5 to 20. It will be terribly big number. Okay, so first row again, but second column here. So minus 1 plus 5 to the power of 20. That's it with the first row. It means that it's time to move to the second row in the first matrix. So second row and first column. Minus 3 times 1 will be minus 3. And this times this will be plus 3 times 5 to 20. And the last one. last row from here and last column from here will be 3 plus 5 to the power of 20. That's it. This is our answer. It's not necessary to, to move 1, 4 inside of the matrix. The answer looks very beautiful. I'm quite happy with it. So this is how the process looks like. Quite a long algorithm, but all the separate steps are quite easy, quite straightforward. So I don't think that anyone will get daunted. And the benefit of this method is that it's applicable to matrix of any size, 2 by 2, 3 by 3, 100 by 100, whatever. Okay, and now it's time to move to our last topic. Which has the same name, by the way, matrix powers, but with method 2, which is much more beautiful, of course. So matrix powers again, but method, oh, wrong spelling, okay, it doesn't matter so much in mathematics, I hope so. Method 2. I want to make a note that it's only applicable for matrices 2 by 2 only. But you come across this task very often, I mean matrices 2 by 2, so it's quite a useful method. Okay, so what we need to know here? This method is based on the very famous, even spooky theorem of Cayley-Hamilton. Let's just recall this theorem. It's very useful, very beautiful idea. So, Cayley-Hamilton theorem. What does it say? What is so wonderful about it, as I'm saying? So it turns out that if you have a characteristic equation, for example, lambda squared plus b lambda plus c is equal to 0, let it be characteristic equation of your matrix. Characteristic equation. You're pretty familiar with it. We've been dealing with the characteristic equation all the time. So for the matrix 2 by 2, the characteristic equation is always a quadratic equation. So then, what then? It turns out that there is a very spooky fact. If you substitute your number lambda is number, arithmetic value, with matrix itself, this equality will be true anyway. Very strange fact. Look at this, what we did. Instead of lambda, we substituted matrix. It's quite a different object. It has dimensions like 2 by 2 and everything. But all of a sudden, the equality is the same. It's just like a miracle, really. But the only drawback is that, we have issue with dimensions. Look at this. In this equation, all the terms were numbers. This is number, no problem adding up together numbers. But here, every term gets dimension now. So the first term is matrix 2 by 2. The second term is matrix 2 by 2 as well. And this guy is still a number. Oh no, something very bad is happening here now, because we can't add matrices and numbers. It just doesn't make sense. It's like adding oranges and apple, of course. That is why a small adjustment is needed. To resolve this issue, we just multiply this C by identity matrix of the same size. So this was 2 by 2, 2 by 2, and that is why we just, multiplying by identity matrix, nothing changes except for dimensions. So this is just like a way out. So it's absolutely wonderful, Cayley-Hamilton theorem. And it has a couple of corollaries which allow us to find the powers of matrices in a more efficient, more beautiful, and much simpler way. So what is this method? So how to find the powers of matrices? So it turns out that if you need to find the power of some matrix 2 by 2, always highlight this idea. It always looks in the same form. Some coefficient alpha 0 times the matrix itself plus another coefficient alpha 1 times identity matrix. So it was mathematically proved that a to any power always has this form. The only issue is to find these coefficients. These are numbers, coefficients. I'm not sure about my spelling. I better not do this. I'm wasting time on trying to write too many words. Okay, and the question is how to find these coefficients, how to find this alpha 0 and alpha 1. And the answer lies in this Cayley-Hamilton theorem. It turns out that if you take this equation and substitute a with lambda this time, they are interchangeable, as you may guess. So we still get the right equation. So let's do it. Instead of a, matrix A, I just put the number. No, not number, but eigenvalue. I'm rewriting alpha 0 from here. Then again, I've substituted lambda instead of a, plus alpha 1, and I don't need to rewrite this guy. It was just written here for adjusting sizes, adjusting dimensions. So that's it. This is the answer. This is a magic equation which would allow you to find these coefficients alpha 0, alpha 1, which are just numbers. But you know how to do it next. So this is the idea, the general idea. Now it's time to get deeper into the algorithm. How exactly can we use this equation? Because it's obvious that it has two unknowns, alpha 0, alpha 1. And this is a very well-known fact. If you have two unknowns, two variables, you need to find two equations to resolve these situations, right? So how can we find two equations? And the answer is, what is lambda? Lambda is eigenvalue. We have two eigenvalues. So if you substitute these two eigenvalues, we will obtain two equations. So it seems like the situation has been resolved. Okay, let's try. You know what? Maybe. No. I'd better give you an example first, and after that, I make a note, very important note. Okay, so I prepared an example question 4C from this tutorial. Question 4C. So here you have matrix A, 4, 2, minus 1, 1. And the assignment is find a to the power of 20. This is our assignment. And now we are going to do it with a more advanced method, which is Cayley-Hamilton theorem corollary. Not the theorem itself, but its corollary. Okay, so what is our central formula? Just to use this method, you need to memorize this formula or this formula, one of them, not both of them, because they're interchangeable, these guys, a and lambda. So let's start with this formula. I sort of memorized it. So lambda to the power of n will always look like this, plus alpha 1. This is our favorite equation. But to use this equation, we need our lambdas. So it looks like we need to perform the first step. The first step is about finding lambda 1, lambda 2. Okay, let's do it. It's our very favorite, very standard procedure. We substitute lambdas from diagonal elements. Okay, 2, 1 minus lambda is equal to 0. And then 4 minus lambda, 1 minus lambda plus 2 is equal to 0. Again, I'm saving time by not solving this equation. I'm just going to give you answers. So lambda 1 was 2 and lambda 2 was 3, not 5, 3, sorry. Okay, so what we can do now, we can use these lambdas, substitute them into this equation, and we get the system. Okay, let's organize it very neatly. So I'm going to write down these lambdas in a column, and I'm going to substitute them into this equation. Okay. Oh, I forgot to mention that we are dealing with concrete case now. Instead of n, we can put 20 here, right? 20. Okay, so 2. Let's substitute 20 instead of lambda here. Oh, not 20, 2, sorry. 2 to the power of 20 will be alpha 0 times 2 here instead of lambda again, and plus alpha 1. So this is our first equation. The second equation will be 3 to the power of 20 is equal to what? Alpha 0 again times 3 plus alpha 1 again. So as you can see, we did come up with a system of linear equations with two unknowns, alpha 0 and alpha 1. But you know what? We are not going to use Gaussian elimination. No, it would be scary to use it because the system is too simple. You can use methods known from high school. For example, it would be very cool to subtract the first equation from the second one. You know why? Because this guy, alpha 1, will get cancelled out. Very nice method. I really like it. So 3 to the power of 20 minus 2 to 20 will be the left-hand side as a result. Here we have 3 minus 2 will be just alpha 0, and this guy just disappears. So we immediately got alpha 0. Very nice, very nice. And to get the second unknown, which is alpha 1, you can use either the first equation or the second one. Is the second? It doesn't matter. I'm going to use the second or the first one. I can solve the first equation for alpha 1 first, which will be 2 to 20 minus 2 alpha 0. And now I can substitute this result for alpha 0 to this equation. In parentheses, of course, 3 to 20 minus 2 to 20. And of course, it needs some simplification. So let's just simplify it. It will be 3 times 2 to 20 minus 2 by 3 to the power of 20. So this is our alpha 1. Let's put a frame around it, just not to lose it. Okay, so now we are ready to do what? We are ready to switch to the second step, which is about calculating the power of the matrix already. Okay, step 2. Step 2 will be the last step, the final step. So what do we do now? You know what? I'm going to rewrite, to copy this equation here. Lambda alpha 0 lambda plus alpha 1. And according to wonderful and spooky Hamilton theorem, we can substitute this lambda by our matrix A. So let's do it. A to the 20, power 20, alpha 0 times A plus alpha 1. And for adjustment, we just write this identity matrix. Okay, and now we already know alphas. We can substitute it, but you know what? I prefer not to substitute them immediately because it will involve a lot of writing. I'll better substitute these matrices. So alpha no 0, matrix A was 4 2 minus 1 1 plus alpha 1. An identity matrix of the same size looks like this. Now again, I'm not gonna substitute these alphas because they look pretty daunting. I can just do these matrix operations. So it will be 4 alpha 0 plus alpha 1 in the top left corner. Here we have only minus alpha 0. Okay, it looks like okay. 2 alpha 0, and finally alpha 0 plus alpha 1. And you know what? This is our answer already. This is our solution. And I feel sort of lazy to substitute these big expressions for alpha 0, alpha 1. You know, you can do it like this, where. So this will be our answer, and where alpha 0, you can rewrite them here, 3 to 20 minus 2 to 20, and alpha 1 is equal to 3 times 2 to 20 minus 2, 3 to 20. I think that this form of answer is quite acceptable. It looks very concise, and it doesn't involve a lot of writing. I'm sure that I would have spent another 2 minutes just to rewriting all this. No, it doesn't make sense to do it. Oh, sorry, I'm not showing the full screen. So as you can see, this method is much more appealing, of course, much more appealing. But remember, it works only for 2 by 2. Even though there is a generalization of this method for cases 3 by 3, but it's somehow it's out of scope of our tutorial, and that is why you can have a look at your study guide. Everything is been explained there, or maybe even in the lecture. But you know what? There is a very important note here. No, I can't read this note. Note to this method. Note to this method. You know what? Sometimes you may come across a very strange, very daunting situation. You definitely need 2 lambdas, lambda 1, lambda 2, to obtain 2 equations. It's a very crucial part of this method. But sometimes you maybe you already know about it. Sometimes you come across a situation when you have only 1 lambda. Mathematicians call this situation repeated root, but it doesn't matter. The name doesn't matter. The fact remains that you have only 1 lambda, but you need 2 equations. What do you do in this case? Let's just discuss it. So let we have a situation when our 2 lambdas coincide. It's just 1 lambda. Let's denote it by lambda. The question arises as to how to obtain the second equation. Because you can still substitute this lambda into our favorite equation. But how to get the second equation? So how to obtain the second equation? The second equation. No room for it. Okay, let's write down the first equation first. Lambda to the power of n alpha 0 times lambda plus alpha 1. So, and then says you can differentiate this. You can find the, so this is the first equation, okay? And how to get the second equation? I'm rewriting this one again. And then the answer is that you can take the derivative of this equation of the both sides with respect to lambda. Lambda is unknown here. So this is the answer. Let's do derivative. So derivative of the left-hand side is n times lambda to the power of n minus 1. And it's equal to just alpha 0. So this is going to be our second equation. That's it. So this is our usual first equation, and this is the second equation. And I think that I have some time left. Maybe we have 10 minutes left, so maybe I can use like 5 minutes to go over one more example. Okay, and the next example involving this particular case will be question 4b. Yeah, it's question 4b. You have matrix A there, which looks like 1, 0, 1, 1, and the assignment is the same. Find A to the power of 20. So let's try and do it. So what do we need now? We need our central equation. I'm going to rewrite it from here, but substituting 20 instead of n at the same time. So lambda to 20 is equal to alpha 0 times lambda plus alpha 1. I'm doing it too early. I need to find my lambdas first, of course. Okay, let's do it quickly. 1 minus lambda, 0, 1, 1 minus lambda. Look at this. 1 minus lambda squared is equal to 0. You immediately see that you have only one lambda, of course. And that means that you need to obtain the second equation by differentiating this one. So just let's take a derivative of the both sides. So I'm going to write it in more detail just in case, because this is the first time you encounter this interesting case. So let's write it like this, prime here and prime here. And so it will be 20 times lambda to the power of 19, which is equal to alpha 0. So this is our second equation, but unfortunately I ran out of paper again. Very frustrating. The screen has limited size, unfortunately, unlike the whiteboard. That is why what I'm going to do, I need to copy these two formulas in the frames to this page, to the screen actually. So let's do it. So the first formula was this one, and the second formula was this one. And we have a lambda is equal to 0. So it's very easy to get this system. We already have it. So let's substitute lambda by 1. So on the left-hand side, you will have 1 to power 20, which is still 1, is equal to alpha 0 times 1. No one writes these things. 20 is equal to alpha 0. As you can see, the system is so easy. So we already actually have alpha is equal to 20, and alpha 1 will be minus 19. So very nice. Everything looks nice. And now it's time to move to the second step, which is about finding the power of matrix already. So our favorite equation is this one, but we need to rewrite it in a matrix form due to Hamilton-Henry theorem. So instead of lambda, I'm substituting A here. A to the power of 20 is equal to alpha 0, copying everything. Lambda, instead of lambda A, plus alpha 1 gets copied, and times identity matrix to adjust the sizes, the dimensions. Okay, and again, just like in the previous example, I'm not in a hurry to substitute alphas. I'm just substituting matrices here. I lost my matrix. No, I found it again. Too many papers on my desk now. So it was 1, 0, 1, 1. So this is matrix A plus alpha 1 and identity matrix. 1, 0, 0, 1 is equal to what? Is equal to alpha 0 plus alpha 1. This has been the top left element. The second element will be just alpha 1. This will be 0. And this will be alpha 0 plus alpha 1. And now it's time to substitute our calculated values, which are minus 19 and 20. So this will be 1. This will be minus 19, really. It looks like I made a mistake somewhere. Yeah, because, there is a mistake. It's alpha 0. Look at this. I made a careless mistake. Okay, so it's going to be 20. This is 0, and this is 1 again. So this is it. This is it. We are finished with this task. You know what? We have 6 minutes left. Maybe it's not a good idea not to wind up immediately, but you know, it never hurts to make a sort of a little review of what we learned today. Let's make a review. Matrix powers. Let's make a review, a summary. Just to see the whole picture in the form of diagram. So you are given some matrix A, square matrix, of course, and you are asked to find the power of matrix n, A, power of n. How can it be done? It can be done in 2 ways: the first method and the second method. Method 1 and method 2. We have 2 methods. Method 2. Okay. So the first method is universal. It's suitable for matrices, any square matrices, any size, and so on. And it involves using the formula, which is a to the power of n is equal to m times lambda to the power of n and m minus 1. So that's it. The drawback of this method is it's quite lengthy. It requires a lot of calculation, but the benefit is that it's just suitable for any size of the matrix. So it's universal. And the second method was suitable only for 2 by 2, only unfortunately. But it's so nice that everyone always goes for this method. So what does it involve? In short, how can we describe this algorithm in short? So let's start with this equation. You need to memorize this equation, alpha 0 lambda plus alpha 1. From this equation, you find alphas, find alpha 0 and alpha 1. You know how to do it now. We are not going into details. We just describe the outline of algorithm. After that, you almost copy this equation, but substituting matrix A instead of lambda, and adjusting the size a little bit using this trick. And that's it. So this is the short description of this second method. But remember, it has its limitations, unfortunately. But if you really like this second approach, you can turn to our study guide. And the similar formula, but much more complicated, of course, is described there for the case 3 by 3, or at least the process is described, how to get this formula. So if you're really interested in going deeper into this subject, you're welcome. But other thing that you will be given, you will be asked to calculate power of A in case of 3 by 3 by this method. Usually they just, like you to do it by this method. So, okay, 3 minutes left, sorry. I'm running out of time. It looks like it's time to wind up. If you don't have any questions, of course. Everyone is silent, so probably it means that everything is clear, hopefully. So let me remind you that our next tutorial will be on campus this time, in the same lecture theater. So if you don't have any questions, I'm going to leave this tutorial. Okay, thank you. You're welcome. And so you can always watch this tutorial once again, because it has been recorded. Yeah, awesome. See you next week. Okay, and you are feel free to send me emails if something is still very unclear to you. Okay, bye bye next time.